This amplifies the input without inverting it, multiplying the voltage by 3, using an op-amp. The op-amp attempts to keep its two inputs at the same voltage. One is at the input voltage, so for the other one to be the same, there must be a voltage drop across the 1k ohm resistor equal to the input voltage. The 2k ohm resistor has the same current across it, so the voltage drop must be twice as large, by Ohm's law. So the output voltage is equal to the input plus 2x the input, or a total of 3x the input. Non-inverting operational amplifier. The second basic configuration of an operational amplifier circuit is that of a non-inverting operational amplifier design. In this configuration, the input voltage signal, VEN, is applied directly to the non-inverting, plus, input terminal, which means that the output gain of the amplifier becomes positive in value, in contrast to the inverting amplifier circuit we saw in the last tutorial, whose output gain is negative in value. The result of this is that the output signal is in phase with the input signal. Feedback control of the non-inverting operational amplifier is achieved by applying a small part of the output voltage signal back to the inverting input terminal via RF, R2 voltage divider network, again producing negative feedback. This closed-loop configuration produces a non-inverting amplifier circuit with very good stability, a very high input impedance, RIN approaching infinity, as no current flows into the positive input terminal, ideal conditions, and a low output impedance, route as shown below. Non-inverting operational amplifier configuration. In the previous inverting amplifier tutorial, we said that for an ideal op-amp no current flows into the input terminal of the amplifier and that V1 always equals V2. This was because the junction of the input and feedback signal, V1, are at the same potential. In other words, the junction is a virtual earth summing point. Because of this virtual earth node, the resistors, RF and R2 form a simple potential divider network across the non-inverting amplifier, with the voltage gain of the circuit being determined by the ratios of R2 and RF as shown below. Equivalent potential divider network. Then, using the formula to calculate the output voltage of a potential divider network, we can calculate the closed-loop voltage gain, AV, of the non-inverting amplifier as follows. Then the closed-loop voltage gain of a non-inverting operational amplifier will be given as. We can see from the equation above, that the overall closed-loop gain of a non-inverting amplifier will always be greater but never less than 1, unity. It is positive in nature and is determined by the ratio of the values of RF and R2. If the value of the feedback resistor RF is 0, the gain of the amplifier will be exactly equal to 1, unity. If resistor R2 is 0, the gain will approach infinity, but in practice it will be limited to the operational amplifier's open-loop differential gain, AO. We can easily convert an inverting operational amplifier configuration into a non-inverting amplifier configuration by simply changing the input connections as shown. Voltage follower, unity gain buffer. If we made the feedback resistor, RF equal to 0, RF equals 0, and resistor R2 equal to infinity, R2 equals infinity, then the circuit would have a fixed gain of 1, as all the output voltage would be present on the inverting input terminal, negative feedback. This would then produce a special type of the non-inverting amplifier circuit called a voltage follower, or also called a unity gain buffer. As the input signal is connected directly to the non-inverting input of the amplifier, the output signal is not inverted, resulting in the output voltage being equal to the input voltage, Vout equals VEN. This then makes the voltage follower circuit ideal as a unity gain buffer circuit because of its isolation properties. The advantage of the unity gain voltage follower is that it can be used when impedance matching or circuit isolation is more important than amplification, as it maintains the signal voltage. The input impedance of the voltage follower circuit is very high, typically above 1 mΩ, as it is equal to that of the operational amplifier's input resistance times its gain, RIN x AO. Also, its output impedance is very low since an ideal op-amp condition is assumed. Non-inverting voltage follower. In this non-inverting circuit configuration, the input impedance RIN has increased to infinity and the feedback impedance RF reduced to 0. The output is connected directly back to the negative inverting input, so the feedback is 100% and VEN is exactly equal to VOUT, giving it a fixed gain of 1 or unity. As the input voltage VEN is applied to the non-inverting input, the gain of the amplifier is given as. Since no current flows into the non-inverting input terminal, the input impedance is infinite, ideal op-amp, and also no current flows through the feedback loop, so any value of resistance may be placed in the feedback loop without affecting the characteristics of the circuit, as no voltage is dissipated across it, 0 current flows, 0 voltage drop, 0 power loss. As the input current is 0 giving 0 input power, the voltage follower can provide a large power gain. However, in most real unity gain buffer circuits, a low value, typically 1 k ohms, resistor is required to reduce any offset input leakage currents, and also if the operational amplifier is of a current feedback type. The voltage follower or unity gain buffer is a special and very useful type of non-inverting amplifier circuit that is commonly used in electronics to isolate circuits from each other, especially in high-order state variable or Salenki type active filters, to separate one filter stage from the other. Typical digital buffer ICs available are the 74LS125 quad 3-state buffer or the more common 74LS244 octal buffer. One final thought: the closed-loop voltage gain of a voltage follower circuit is 1 or unity. The open-loop voltage gain of an operational amplifier with no feedback is infinite. Then, by carefully selecting the feedback components, we can control the amount of gain produced by a non-inverting operational amplifier anywhere from 1 to infinity. Thus far we have analyzed an inverting and non-inverting amplifier circuit that has just one input signal, VEN. In the next tutorial about operational amplifiers, we will examine the effect of the output voltage, VOUT, by connecting more inputs to the amplifier. This then produces another common type of operational amplifier circuit called a summing amplifier, which can be used to add together the voltages present on its inputs.